Good morning. So I'm going to try and give as much of a whirlwind tour of the entire field of dimension reduction as I can in the time available. We're going to have to skim a little bit, but that's fun. Okay, so first up, after I submitted the talk, came to learn that Bluffer's guides are not necessarily as common a term in North America as they are from England and New Zealand, where I'm from. So just so everyone knows what they mean, think Cole's notes, but for any topic. So it's really meant to be a sort of a lighthearted, humorous survey of a topic to just give you an overview of the whole subject. All right, so that means the focus of this talk is really on the core intuitions and core ideas rather than the nitty-gritty details of exactly how all these algorithms work. I want you to come away with an understanding of dimension reduction broadly and sort of how you can think about it rather than necessarily particular details of how any given technique works. So that means I'm going to introduce a little bit of extra notation which is going to be really useful repeatedly, and that's the red star. So sometimes technical details really matter, but they're not worth getting into because by the time you've explained all the technical details, you've lost the point of what you were trying to explain in the first place. So if I just want the big picture idea, and there are some technical details that make that statement not technically true, but morally it's the right thing, I'm just going to put a red star by it. So it's essentially true, but you know, there's lots of technical details that make it not exactly true. Okay. So, first of all, there are only two dimension reduction techniques. So, in practice, that means really there's either matrix factorization or neighbor graphs, and that's pretty much all there is other than feature selection techniques and one special case that I'll mention in a minute. So, matrix factorization really means this huge, broad class of techniques. It's everything from topic modeling to word embeddings, plain old PCA, all kinds of other probabilistic techniques. It covers a huge swath of algorithms, but they can all be thought of under a sort of very simple, basic, single matrix factorization framework. And so in the end, what really matters is what matrix you construct to factor and how you compute the sort of reconstruction error of your factorization and what constraints you put on that optimization. You work those out and that will give you these different sorts of algorithms. Neighbor graphs is, again, a very broad class of techniques. This is everything from spectral embedding to TSNE to large viz. UMAP falls in this category as well. These are all basically built around an idea that you're going to build a graph out of your data and then you're going to embed that graph in a low dimensional space, and at the end of the day that's all you're really doing. All the detail comes into how you construct the graph, how you lay out that graph. So the odd one out here that I mentioned is autoencoders. Linear autoencoders fit nicely in matrix factorization, but the autoencoders are a very broad class of things, and various families of autoencoders are not going to be phrased as matrix factorization at the end of the day. So they're kind of an odd one out, but I'm going to push that aside because I really want to just focus on the fact that you only really need to know two things to know all there is to know about dimension reduction. So let's start with matrix factorization. So first we'll look at what it is, and then we'll work through a number of examples covering a bunch of different algorithms and sort of give you an idea of how you can specialize it into all these different specialized algorithms that exist, and give you some idea of the scope of algorithms that you can actually build out of this very simple idea of just factoring a matrix. Okay, so the goal of matrix factorization, pictorially, is we want to express a matrix as approximately a product of two smaller matrices. That's all we're doing. So in terms of dimension reduction, the blue matrix is our data. That's the source data we've got in sort of each row is a sample, each column is a feature, and we want to sort of factor that into a representation multiplied by some archetypes. So you can think of the representation, that's your low dimensional representation. The archetypes are sort of the basic forms, the exemplars that you're going to use to reconstruct the original data. So looking just at a single row, you can think of a single row of your data, a single sample, as being represented as one row of your representation. There's a corresponding representation for each sample, and it's going to be multiplied by or act on the entire matrix of archetypes. So breaking that out, what you're actually getting is a single row expressed as a linear combination of these archetypes, and the coefficients of that linear combination are your representation, your low-dimensional representation. So that's all we're really doing. We're expressing our data as a combination of these archetypes, and that's matrix factorization. Now, math makes this pretty because I just get to write this instead of complicated pictures, but as matrices, this is our data. X is approximately equal to U times V. Now, the upside of math is that this makes it all nice and compact. The key here is that approximately equal to. That's going to be pretty much everything that goes on in these algorithms. How do we define approximately equal to? Depending on how you define it, you can get lots of different things. So what we can do is turn this into a different problem, turn it into an optimization problem. What approximately equal to is going to mean is we're going to try and minimize some notion of error or loss. So we can define it this way. We're trying to minimize this loss between our original data and our reconstructed data subject to some constraints. And exactly how we define that loss and what those constraints are going to give us all these different matrix factorization techniques. Now, if you're interested in this mentality of thinking about things, I highly recommend you go and read the Generalized Low-Rank Models paper by Udall et al. It's a fabulous paper. It's hideously long, but don't be intimidated. It's actually really easy reading. It's well written, very easy to follow, and it gives you a really broad understanding of how general matrix factorization can work. Okay, so let's go through some examples. Let's start with principal component analysis because it's sort of the standard approach for dimension reduction using these sorts of techniques. And really what that means is that it turns out that just mean squared error can do a lot for you, especially if you get around to playing with the constraints. So classical PCA is just taking that loss and writing the loss as the squared error between each of the terms. And we're just going to sum it up over all the entries. So that is PCA. Now, in practice, PCA is computed by fancy linear algebra techniques, but this is what it's computing, so you can think of it in these terms. This is your loss. You're just talking about the squared error. One of the problems PCA can run into is that it's sometimes hard to interpret, especially if you have your low dimensional representation has a lot of dimensions. You're reducing to maybe 20, 50 dimensions. That's a lot of different archetypes you're combining if you're trying to think of it as a linear combination of archetypes. And so it's sometimes hard to wrap your head around, oh, well, I have 0.13 of this feature archetype and 0.78 of that one, and it gets very complicated to think about. So you can constrain your optimization so that you're only going to have so many archetypes in each representation actually showing up. So that's as simple as adding constraints to our optimization. So if we add some constraints, we actually get a whole brand new technique called sparse PCA, which is entirely different, except it's not. You're just adding some constraints. And so what we're going to constrain is the number of non-zero entries in our representation U. Each row of U is only allowed to have k many non-zero entries. So that's going to make it much more interpretable because I'm going to be able to say, yeah, it's a linear combination of these archetypes, but any given representation is at most k many archetypes. And you can make k a lot smaller than the dimension you're reducing to. That makes it much more interpretable, easier to understand what's going on. Okay. Fewer archetypes was good. Let's turn the dial to 11 and constrain it as much as possible. What if I said I only want one archetype to appear per row? Then we actually get k-means clustering. So this gives you some idea of how general this sort of framework is. We've just managed to go from PCA to k-means clustering by just turning a dial on how I do my constraints. So in practice, what I'm going to get is a matrix U, which has one non-zero entry in each row. The index in that row is going to be the cluster label, and the archetypes are literally the cluster centroids from k-means. Now, this is not how you're going to compute k-means, but this is the result you're going to head toward. All right, let's try some different algorithms. Non-negative matrix factorization. So, especially in the case when your data is all positive, it can be kind of hard to think about subtracting components off. PCA allows the coefficients to be positive or negative, and it's easy to think about composing the archetypes together. I'm adding this, and then it's the addition of this and the addition of that. But then if I'm subtracting away things, that's harder for people to wrap their brains around. So if you want to make an interpretable thing that's easier to present to other people, if it's purely an additive composition of the archetypes, that's a lot easier to think about. And that's all non-negative matrix factorization is doing. It's PCA, but I'm just going to constrain my U and V matrices to only have positive entries. I'm just sticking constraints on PCA. That's all it is. And this is non-negative matrix factorization. Again, all the details of how to compute this are a different matter, but this is what it's doing. Now, most non-negative matrix factorizations also have a KL loss option, which looks something like this, which looks really weird, but we'll come back to that after we've had a look at exponential family PCA in a minute, and this will make a lot more sense, as well as why the constraints work out quite as well as they do. So let's move straight in. Exponential family PCA is kind of a fancy way of generalizing all of this with a bunch of probability theory. So the goal here is, what if I knew more about my data? What if I had some sort of model for how my data was generated? Suppose my data, each entry was a count of something. For each feature, I've got counts. If I ask a statistician, she'll tell me that I should probably model that with a Poisson model. So can I incorporate that extra information into my matrix factorization? So here the goal is to look at theta, which is going to be my product of U times V, my reconstruction, not as a reconstruction of X, but as a reconstruction of model parameters that will make X the most likely thing to see. So the loss term is now going to be the negative log likelihood of observing my data under this model that I'm reconstructing. So I want a low rank model that makes my data as likely as possible. So how do we parameterize that? Well, the easy way to go is the exponential family of distributions. It's a nice, easy to parameterize entire family of distributions that covers all your favorites like normal distributions, Poisson, Gamma, Dirichlet, Bernoulli, the lot. So there's a nice big family, and it's easy to work with because the negative log likelihood is proportional to this, where this G function of the theta parameters is really just something you can look up for each individual different distribution and plug in to your loss. So let's test this out and see if this is actually going to give us anything meaningful. So what if I told my stats friend that my data was normally distributed? They're going to tell me to use normal matrix factorization, where normal is my probabilistic term there. So for the normal distribution, G is just half of the L2 norm of the rows. So it's half the reconstruction U times V squared. And I'm going to have no constraints as per normal. Okay, that doesn't look like anything that I would understand very easily, but I can do this. Because the Xij are my data, they're never changing. Those are constant. So I can add on Xij terms, and that won't change the minimization I'm doing. So I can add on this half Xij squared term, and that doesn't change the minimization or the objective that I'm effectively computing there. Okay, that looks weird, but what am I doing? Well, if I complete the square, then magically it turns out that normal matrix factorization is PCA. Or in other words, PCA is just what you would do if you assume your data is normally distributed. This should give you a warm fuzzy feeling that this is actually working entirely as we expect, because normal distributions are probably what you might want to guess if you know nothing else. Okay, so that's great, but let's go back to count data. What if I had count data and I wanted to use Poisson distributions? What does Poisson matrix factorization look like? Well, for Poisson matrix factorization, the G is just the exponential function. So you get out a loss function that looks like this. And now you should think back to the KL loss for the non-negative matrix factorization and realize that this looks almost the same, except we swapped an exp and a log, but in a very obvious way. And the catch here is that now I have no constraints. With non-negative matrix factorization, I had constraints on my U and V so that everything came out positive. That's basically saying the lambda parameter for a Poisson should be a positive number. The arrival rate should be positive. If you reparameterize your Poisson distributions with log lambda instead, then you get this, and now I can do the whole thing with no constraints, which makes for a much cleaner, easier optimization to run. We lost some of the interpretability issues with non-negative matrix factorization, but we gained a much easier optimization problem out of it. And you can play this game with anything. Binomial matrix factorization, Bernoulli matrix factorization, beta matrix factorization. Pick your favorite distribution that you think describes your data well. You can plug it into the formula, work out what you should get as your loss function, and magically you have yet another matrix factorization algorithm that is dimension reduction specialized to your type of data. So this is a really powerful technique. Okay. What about latent Dirichlet allocation? This is not dimension reduction. This is like topic modeling with like crazy Bayesian graphical models that are complicated. Well, let's work through it. What if my theta parameters were multinomial distribution? So each row of my reconstructed matrix is parameters for a multinomial distribution. Okay. I can work out what multinomial matrix factorization looks like. Now I've elided some math, but you can push this through and this is pretty much what you'll get out. This is what multinomial matrix factorization will look like. The loss term just follows through from that negative log likelihood, and I'm going to have to stick some constraints on my reconstruction so that my u times v actually give me things that look like parameters of a multinomial distribution. That's great. But we can go a little better. We can add a latent variable k. So the goal here is that if I make u, my matrix u, a multinomial over this k, and then my v is provides k as a multinomial over my features, then when I multiply these two things together, magically I get out the result being parameters for a multinomial distribution. So where previously here I had these odd parameters on u times v, I can swap that for constraints on u and constraints on v separately that will guarantee I get the right constraints on my multiplied together thing. But we get more. We get actually some quite nice interpretability out of this, because now each row of u, our representation, is going to be a multinomial distribution over archetypes. So I can interpret a row of my u, in other words, a point in my low dimensional representation, as a distribution over archetypes. And each archetype is going to be a distribution over my features. So this is nice. It's interpretable. We can understand what it's doing. Stick all that in, and we get probabilistic latent semantic indexing, which looks just the same. I just changed my constraints a little. Okay, that's great and powerful, and it has all that interpretability. Vectors of probabilities of archetypes, and each archetype is a vector of probabilities of features. That's pretty cool, but we can be even more hip and trendy. Let's be Bayesian, and we can apply a Dirichlet prior over the multinomial distributions for u and v and just take a step back. Okay, and that's LDA. That's all LDA is. Now, there's a lot of details I've carefully swept under the rug, but this is all you need to do to understand basically the mechanics of what's going on in LDA. It's a matrix factorization in a probabilistic sense where I'm just thinking of everything in terms of multinomial distributions. And that's why it works so well on if you take a bag of words view of a document, I've just got counts of words appearing. Well, a document is a count of all the different words, counts of words appearing in the document. That's a multinomial distribution. This is entirely the right way to model this. So if you can come up with a model for your data, you can use matrix factorization techniques to do all kinds of surprisingly fancy things that really are just matrix factorization under the hood. So this should give you some idea of how incredibly powerful matrix factorization can be. We started with something as simple as PCA, and we've ended up with really quite sophisticated techniques that can do quite powerful things, but it's all still the same basic idea under the hood, and it's pretty easy to understand when you think of it in those terms. Okay, how about neighbor graphs? So neighbor graphs cover a wide range of algorithms. Some of them build graphs with edges between all the points even, so neighbor graphs is perhaps not the best term, but it's the best term I could come up with. And the catch here is that the resulting algorithms are a lot more diverse than matrix factorization. Matrix factorization, there was sort of a consistent story. I could write everything in the same terms. Neighbor graphs, things look very different, but there are some really core common themes at the end of the day. which is that you need some way to build a graph and you need some way to embed that graph. So let's have a look at some of the intuition behind this. So here's some data, and there's some low-dimensional structure in that data that you can hopefully see, but a linear approach like PCA is not going to find it. But if I draw a graph where I link each point with an edge, if it's in the k nearest neighbors of that point, magically this graph seems to have uncovered that structure that I wanted to find. So that's the intuition for these sort of neighbor graph type approaches. And one can be either more or less formal about how you go about describing this. You can either hark to this intuition, or you can go and use fancy topology to say that, no, this is actually mathematically doing the right thing. But this is the guts of what's going on. Now, one caveat, and the reason there's a red star on both these pictures, is that this is the intuition of what's going on, but this picture is really deceptive because it's convenient in 3D where you can see what's going on and get an intuition that does not scale to higher dimensions and the sort of weirder structures you can get in your data in higher dimensions. And so while this gives you an idea of what's going on, the intuitions you get don't necessarily work out as well as you'd like for actual real data. Okay, so the questions you need to ask are, how do I build the graph and how do I weight the edges of that graph? If you can work that out, that'll get you a long way through the algorithm, and we'll look through several different algorithms in a minute. And then how do I lay out that graph in low dimensions? There's lots of ways of going about that. We'll go through a few as we look through some of the different algorithms here. So isomap is one of the early approaches to this neighbor graph style approach to the problem. So here we're going to take the k nearest neighbors and we're going to weight them by the ambient distance in the high dimensional space we work in. So assuming we're in Euclidean space, I'm just going to put a weight on each edge, which is the Euclidean distance between the points. And now I'm going to build a complete graph. That means a graph with edges between all possible points, weighted by the shortest path lengths on that graph that I had. So in pictures, I have one red point, I have another red point. I want to say how far apart are these red points, what's the weight I want to give to the edge between these two red points, and it's going to be the path, the length of the path through the graph that gets me there in the shortest route. That's it. And then we're going to build an adjacency matrix out of the graph. And adjacency matrices aren't anything fancy. They're just the weight of the edge, or 0 if there's no edge. And that's good. So now we have a matrix. So how do we turn a matrix into a low-dimensional representation? You should know this by now. We factor the matrix. That's exactly what they do. They just take the largest eigenvectors. Okay, so what about spectral embedding? They have a different approach to weighting the edges. They're going to take a kernel over each point and weight edges according to that kernel. So the further away points are, the lower the weight I'm going to apply to them. Now this has a nice feature because you notice that adjacency matrix representation, I had 0 if I had no edge, but I had a really big number if points were really far apart. It'd be nice if I didn't have to have all the edges filled in. I could just have edges that are really far apart, have a very small number that's close to 0, sort of smooth everything out, and everything works better. So this is the idea behind this. You're going to build a kernel over each of the edges, some sort of like Gaussian RBF type kernel, and work with that. And then we're going to compute this thing called the graph Laplacian, which is a complicated formula. There's a bunch of them, but what you can think of it as, I have these weights attached to each edge, and I basically want to divide out by the marginals of either the rows and the columns so that I sort of normalize things out. That's really what's going on there. And then we have a matrix again. So we factor the matrix. This time we're going to take the smallest eigenvectors because we swapped everything around. We had small numbers instead of large ones. There's a red star there. There's one of the eigenvectors you actually ignore, but that's okay. All right. TSNE, T-distributed stochastic neighbor embedding, which is often described in probabilistic theory terms, but it's really a graph algorithm as well at the end of the day. So with spectral embedding, we used a single bandwidth for the kernel everywhere across all the data. With TSNE, we're going to vary the bandwidth, vary how wide I'm going to make that kernel according to the density of the data, essentially. Now, there's some complicated formulas for how exactly one does that, but that's not really what you need to sort of worry about. Mostly, we're just going to take the k nearest neighbors, and we're going to vary the size of the kernel to match roughly with those k neighbors. Then I'm going to normalize outgoing edge so that all the outgoing edge weights sum to 1. That's just a thing I'm going to do. And then I'm going to symmetrize the whole thing so that I'm going to, if I have two edges with different weights between 2 points, I'm just going to average them. And then I'm going to renormalize the whole thing so that all the edge weights in the whole graph sum to 1. Okay, that's a complicated bunch of manipulations, and it's not exactly obvious from my description why anyone would want to do them. There are justifications for all of this. They're in the TSNE papers. You're more than welcome to read through it. But what I want you to take away from this is that exactly how to weight the edges matters. TSNE works really well, and it works well because it goes to a lot of trouble to work out a good way to provide edge weights that really work. And so modern techniques will jump through a lot of hoops and have a lot of complicated operations to weight these edges in certain ways to make the algorithm work well. Okay, so how do I lay out the graph? Well, I use a force-directed layout this time. So this is actually a standard approach in laying out graphs in network science or graph practice as opposed to graph theory. And so what's going on here is I have a graph, and nodes have a repulsive force between them. So, is that showing? Yes. Okay, so they're going to spread apart, and edges have an attractive force that are going to pull things together. And that's all that's going to be going on. I'm going to push nodes apart, generally with a standard repulsive force, and I'm going to pull nodes together along edges with an attractive force. And how you compute those forces are going to change your exact algorithm, but you can think of it as kind of the repulsive force is often described as like an electric field that's repulsive between the points, and springs for edges that pull everything together. See, it's like a spring algorithm. And that's all you have to do. You're going to have decaying forces so that the further apart nodes are, the less repulsive force there is between them and so on. But at its core, you're pushing nodes apart in general, pulling them together along edges, and that's all you have to do. So here's this is the TUT graph, and if you use this algorithm, standard force-directed layout type algorithm, it sort of pushes everything around, pulls things together along the edges, and it sort of slowly but surely relaxes into a nice layout. And this is really all TSNE is doing, is this sort of force-directed layout has a particular way of computing the attractive and repulsive forces, but that's the specifics. For the core ideas, all it's doing is this. Okay, so finally, UMAP, Uniform Manifold Approximation and Projection. How does it work? Is it a k-neighbor algorithm? Yes, it is. Really, we just take the k-nearest neighbors, weighted according to a bunch of fancy math. And it turns out that it's not very elucidating without a whole lot of background to describe what those manipulations are. TSNE was bad enough to describe the manipulations. This won't help much. But you can look up my talk from SciPy this year if you want more details on how this is actually computed and the intuitions behind why you would go through the crazy manipulations we have. But this is the general idea. The core of it is that at the end of the day, it's kind of similar to TSNE, but we're going to derive a different kernel via different math with different approaches. And then we're just going to use a force-directed layout. Now we're going to, again, different math went into it, so we're going to derive different forces, so the force-directed layout is going to be a little different. But fundamentally, we're just still doing the same force-directed layout of a graph, and that's the core idea behind UMAP. Okay, so in summary, dimension reduction is really built on just a couple of primitives. Matrix factorization, neighbor graphs, that's really everything to it. And framing a problem as a matrix factorization or a neighbor graph algorithm captures most of the core intuitions of those algorithms. So this is sort of a general framework for understanding most dimension reduction algorithms. If you come across a new algorithm and you want to try and understand it, what you want to do is ask yourself, can I frame this as a matrix factorization problem? Is this really just building a neighbor graph in some complicated way that they hid in their description of it? And if so, what matrix are they factoring? How are they, what's their loss function? What are their constraints? Or what graph are they building and how are they laying it out? And if you can work through those aspects of it, you can actually understand almost any dimension reduction technique pretty quickly, at least at an intuitive level for what's really going on. So this is a great way to understand dimension reduction in general. All right, questions? Do we need?
Yeah, we probably don't have enough time for this, but I mean, you clearly are very short on details for UMAP. Is there any way you could explain like the basic intuition, like or give some references or some suggestions for understanding the basic intuition behind these things, like even for TSNE, like it's a little unclear to me, like so you describe the scheme, but like what is the intuition behind this scheme? Like I feel like I have no understanding of why that's a good thing.
That's a fair question, and I won't speak to the intuitions behind TSNE because they write it in certain terms, and I'm less comfortable describing their intuitions. I can explain some of the intuitions for UMAP. So one of the core things that went on there was we had this variable sized kernel. Why would you want to do that is a perfectly good question. And so for UMAP, the answer to that question is that ultimately these neighbor graph algorithms are based on topological techniques. The graphs are really a topological thing, and those topological techniques only work if the data happens to be uniformly distributed on a manifold. And your data probably isn't, at least with respect to the ambient space that the data lies in. By varying the size of the kernel, we're basically adapting the metric on the manifold to make that be true. And so that's the sort of part of the magic sauce that makes all of this work. The catch with doing that is that we now made everything incompatible. All these different patches have a different notion of distance, and we have to somehow glue all that back together. And that's where that recombining. TSNE just averaged things, but there are different ways to think about how to do that. And so you want to glue all that back together. So that's how your operations for building the graph are. It's the same core intuition that went into spectral embedding, where I put a kernel over things and I want similarities between things, but I'm adapting it to deal with the fact that there's these topological obstructions to this algorithm actually working. How do I work around those? How do I adapt the algorithm to make it work in this more general case? Is that okay? Thanks.
Thank you so much for this talk and all of the effort to really kind of paint some big picture and like relationships between things. Have you thought about what relationships exist from a perspective of computational complexity and the ability to do implement these in distributed and/or parallel fashion?
So I'm really a mathematician, so I actually like to think in terms of purely abstract stuff and not in terms of implementation details, although those do come up. And one catch is that these are all wildly different in computational complexity. All those wonderful matrix factorization algorithms, PCA is trivial to compute, relatively speaking, because you can solve that objective function in a closed form with linear algebra like that. There's like, here's what you need to compute. Just do this linear algebra operation. Whereas when I start sticking some of those constraints on, now I just have an optimization problem. If I do some of the probabilistic ones, it's not necessarily even a nice convex optimization problem. And I've just got to compute a whole lot of stuff and try and optimize this. And now it's really hard. So that is one of the catches, is the computational complexity of these in no way matches the sort of easy way you can tie them together in terms of the underlying theory. And that's often why there are so many different techniques, is people want to take different shortcuts to how to solve the computational complexity issues introduced by taking a different idea.
Thanks. I really like the way that you made all the matrix factorization techniques feel the same and the same yoga that went into solving those problems as optimization problems. And so I think there's a kind of obvious question lurking in the neighbor graph situation. So we're going to eventually find ourselves at a matrix factorization problem, but that first step where we're picking different ways of constructing the neighbor graph, how do we turn that into the same old optimization problem to construct those neighbor graphs? Because there are different strategies to construct them. What's the underlying generalization?
I think that's a very astute question, because I think that's the research problem that is going into these algorithms now, is what is the right way to think about this to actually come up with a good, clean general theory that you can adapt. And I don't think there are good answers to that. That is an open research problem right now.
I like the intuition you gave from UMAP, where it's like we're scaling these kernels to fit on the right metric for the underlying topology. So I don't know. That got my mind wandering.
Well, obviously, I think that's the right way to go, but.
All right. Well, thank you.
Thanks.